So this is the next video. So in the previous class we have discussed about the Raoult's law. Now we will go to the next topic, that is ideal and non-ideal solution. So in the previous video I have told you what is Raoult's law. Raoult's law is mainly applicable for calculating the vapor pressure of the component present in a solution, because we know that a solution is made up of more than one component. That's why the Raoult's law is useful, or it is used to calculate the vapor pressure of the component of the solution. Means if 2 or 3 components are present, then Raoult's law will tells you about the vapor pressure of individual components. So now in this case we will discuss about ideal and non-ideal solution. So first of all we will start from ideal solution. Ideal solution. So what is ideal solution? What do you mean by ideal solution? Clear? So ideal solution means solution which obey Raoult's law is known as ideal solution. So the solution mixture which obey Raoult's law is known as ideal solution. Clear? And you know about Raoult's law. So next, properties of ideal solution. Properties of ideal solution. Ideal solution. What are the properties of ideal solution? Okay, number 1. So before going to the first property, I want to tell you that in a solution the two things are there, solute and solvent. Okay, so in the solution there are 3 type of interaction is there, because we know that each and every particles are having some intermolecular forces or interparticle forces. So what are the different types of interactions are there? The interactions are, first is the solute, a solvent and solvent, because we take solvent as A, that's why the interaction is called as AA type interaction. Solvent interaction. This is solvent interaction. Solvent interaction. Similarly, B, this is B is considered as a solute. So solute interaction. And when we are mixing solute and solvent, then AB interaction, that is solvent and solute interaction. Solvent and solute interaction. Clear? So there are 3 type of interaction in a mixture of solution, that is AA solvent interaction, BB solute interaction, and AB solvent interaction. So what happens in ideal solution? The AB, that is the solute interaction, solvent interaction, and the solute interaction all are equal to each other. This is the first property of ideal solution, that the solute solvent and the solute interaction all are equal to each other. Means there is no net effect before and after the making of solution. Before or after the making of solution there is no net effect over the solution. Means whatever the effect is there previously in the solution, same effect we can observe after preparing the solution, and that is called as the AB interaction. So these 3 are all same. This is the first property. Second property is the delta V mixing. What is delta V mixing? I am telling you, delta V mixing must be equals to 0. Delta V mixing must be equals to 0. What it means? delta V mixing equals to 0 means before and after preparing the solution, the total volume before preparing the solution and after preparing the solution, the change in the volume will remain constant. The volume will remain constant means before the solution and after the solution the volume remains constant. There it means there will be no change in the volume. There will be no change in the volume. For example, if component A is taken as 50 ml and component B is taken as 50 ml. So this is component A, this is component B before the preparing of solution. At that time this is 50 ml and this is 50 ml. Clear? So after preparing the solution, if it remains 100 ml, 100 ml means 50 plus 50, this is also 100. So before solution total volume is 100 and after solution also the total volume is 100, then it is called as delta V mixing is equals to 0, means before mixing and after mixing the volume will remains constant. The volume will remains constant. This is called as delta V mix equals to 0. This is the second property of ideal solution. Then third property is the delta P mix, means the vapor pressure. The vapor pressure will also remains constant. The vapor pressure also remains constant, means since there is no interaction before and after, means the interaction remains constant, we can say there is no net effect of the interaction before and after the preparation of solution. So the delta V mixing means the change in vapor pressure will remains constant, there will be no more change in the vapor pressure, means the vapor pressure will remains 0. And the fourth property is delta H mixing remains 0. Delta H mixing remains 0. What is delta H mixing? Means before and after the mixing, whatever the change in enthalpy, if that is equals to 0, means no release of heat or no absorption of heat, or we can say there will be no increase of the temperature or no decrease of the temperature, the delta H mix remains 0, means the change in enthalpy remains 0. There is no change in the enthalpy before and after the mixing of the two components or the two solution. Clear? So delta H mix will also remains 0. Clear? Next. So now we will see some example of ideal solution. Example of ideal solution. Example of ideal solution. But remember one thing, there is no such solution which is completely ideal. Any of this parameter may vary. In any of the parameter may vary. So there is almost very few examples are there in which it is completely ideal solution. Still few examples are there under certain circumstances they are considered under ideal solution. But remember, no such solution is there which is completely ideal and follow all this property. But under some circumstances, few examples are there which is considered under the example of ideal solution. That is number 1, benzene plus toluene. Benzene plus toluene. First example is the benzene plus toluene. Second, chloroethane plus bromoethane. And third is the chlorobenzene plus bromobenzene. This comes under the what? Comes under the ideal solution. So these are few of the examples of ideal solution. Now we will come to this graph. Graphically we will explain the ideal solution. So in the Raoult's law, you observe this graph where I have told you, when you are increasing the concentration of component A from 0 to 1, here the composition means the mole fraction is increasing from 0 to 1 of component A. What we can observe, the vapor pressure of component A increases. The vapor pressure of component A increases. Clear? Similarly, when the mole fraction of component B, it is 1 here, when it is decreasing in this direction, means from 1 to 0, because when we are increasing this component, the composition of this one will decreases, or the mole fraction will decreases. So that's why when the mole fraction of component B is decreasing in this direction 1 to 0, we can observe that their vapor pressure will decreases. This is according to Raoult's law. This is according to Raoult's law. So, and this is the P total. This is the P total, that is the summation of vapor pressure of component A and component B. Clear? So that's why we can say that the solution which follow this graph, follow the graph of Raoult's law, that is called as ideal solution. That is called as ideal solution. So whenever the composition is increasing from 0 to 1, means the mole fraction is increasing from 0 to 1, the vapor pressure is increasing. The vapor pressure is increasing. But when the mole fraction is decreasing from 0 to 1 to 0, the vapor pressure is decreasing. It follows Raoult's law. So this is the graph of ideal solution. So this is the graph of ideal solution. Next, next we will discuss about non-ideal solution, with positive deviation. First of all, we will discuss about non-ideal solution. So simply ideal, non-ideal. If we say ideal means it follows Raoult's law, non-ideal means it do not follows Raoult's law. So mixture of solution which do not follows Raoult's law is known as non-ideal solution. Clear? So mixture of solution which do not follows Raoult's law is known as non-ideal solution. So let's start with positive deviation. So non-ideal solution with positive deviation. Their properties. First of all, we will start with properties. What are the properties of the non-ideal solution with positive deviation? So see, properties of the non-ideal solution with the positive deviation. First point, it is very, very important, make it star mark. The first point, that AB interaction means solute solvent interaction is less than AA and BB interaction. AB interaction is less than AA and BB interaction, means the solute solvent interaction is less than solute solute and solvent solvent interaction. What it signifies? It signifies that whenever the solution is prepared, whatever the interaction is there in case of solute solute and solvent solvent, that will be suppressed by the solute solvent interaction. Means here the molecular interaction decreases. It means the molecular interaction, interparticle interaction decreases. That's why the solute solvent interaction is less than the what? solute and solvent and solute interaction. Clear to all? Means here the molecular interaction decreases when we are preparing the solution. Means before the solution, whatever the interaction, after the solution the interaction will decreases. Clear to all? Next, second property, delta V mix. Delta V mix, suppose 50 ml plus 50 ml. In ideal solution it will be equals to 100 ml, but when it is a non-ideal solution with positive deviation, this should be greater than, when 50 and 50 is added, it should be greater than 100. It should be greater than 100. Clear? Means the component A plus B when mixed together, that should be greater than, means it will be greater than 100. It will be greater than 100. Clear? It should be greater than 100. Greater than 100. So delta V mix will be greater than 0. Delta V mix will be greater than 0. Means the change in volume is greater than 0. The change in volume is greater than 0, means when we are mixing two components, suppose 10 plus 10, it should give 20, but it gives more than 20, 20.01, 20.02, 20.025, like this. Some volume increases, maybe in decimal, maybe in very slight amount, then the delta V mixing will be greater than 0, means the change in volume is not equals to 0, it is greater than 0, and that is the second property of positive deviation of non-ideal solution or non-ideal solution with positive deviation. Similarly, third point, the delta P mixing, the vapor pressure will also increases. The vapor pressure will also increases. The change in vapor pressure will be greater than 0. The vapor pressure increases means what? Before the solution, if it is 10, suppose 10 mm, after the solution it is 20 mm, means 20 minus 10, it is 10, so it will be greater than 0. So delta P mixing is greater than 0. Delta P mixing is greater than 0, means suppose if it is delta, before solution it is 10, after solution also the vapor pressure is 10. It means 10 minus 10, it is equals to 0, means delta P mixing is equals to 0 in case of ideal solution. But in case of non-ideal solution with positive deviation, before it is 10, suppose it is 10, after making the solution it is 20. So what happened? The delta P mixing is not equals to 0, because 20 minus 10 it is 10. So the delta P mixing is greater than 0, 10 is greater than 0. That is why the delta P mixing is greater than 0. Clear? Next, fourth, delta H mixing. Delta H mixing, it is also greater than 0. Delta H mixing is also greater than 0. So when delta H mixing is greater than 0, when delta H mixing is greater than 0, means it having a positive value. Delta H having positive value. If delta H mixing is greater than 0, delta H will be equals to positive. It means the non-ideal solution with positive deviation is a endothermic process. Is a endothermic process. Is a endothermic process. Non-ideal solution with positive deviation is endothermic process, because the delta H mixing is greater than 0. It means delta H is positive, hence it is a endothermic process. Clear? Now we come to the graph. Come to the graph. So what happened in the graph? Here it was told the delta P mixing, the vapor pressure will not equals to 0. Not equals to 0, it is greater than 0. That is why you can see this is the vapor pressure, this dark line represent the vapor pressure, this dark line represent the vapor pressure of the ideal solution. But when there is a positive deviation, here the delta P mixing is greater than 0, means the vapor pressure is increases. So this dotted line represent the vapor pressure after the solution. Vapor pressure after the solution. So we can see here all the vapor pressure after the solution prepared, it will increases. After the solution prepared, it will increases. So this dashed line represent the original vapor pressure. This dotted line represent the vapor pressure after the preparation of the solution. So we can say the vapor pressure increases. From this equation we can say the vapor pressure increases. That's why here in the graph we can see the vapor pressure increases from their original, according to Raoult's law, or from their original vapor pressure. Clear? So this is the non-ideal solution with positive deviation. Next, so now we see what are the examples of non-ideal solution with positive deviation. What are the examples? Examples of positive deviation, where it shows the positive deviation. So first of all is the water plus ethanol. Water plus ethanol, because we know that in water there is intermolecular hydrogen bond, and ethanol also there is intermolecular hydrogen bond. So their solute and solvent interaction is more than that of solute-solvent interaction. So this is the first example of positive deviation. Second example is water with benzene. Water with benzene. So this is the second example in which you can see that there will be a positive deviation. And the third example is the CH2 plus acetone. So these are few examples, 3 examples of non-ideal solution with positive deviation. Non-ideal solution with positive deviation. Clear? Next. Next we will come to the next point, that is non-ideal solution with negative deviation. What is non-ideal solution with negative deviation? So non-ideal solution with negative deviation means what are the properties we can see? Properties means, number one property, the solute-solvent interaction, means the interaction after the formation of solution is always greater than the solvent-solvent and solute-solute interaction. This is the important point. That before the formation of solution, or before the formation of the solution, solute-solute and solvent-solvent, whatever the interaction is there, that is less than the solute-solvent interaction, because after the solution the interaction increases. After the solution formation the interaction increases. So we can say that the intermolecular or interparticle force of attraction increases after the formation of solution. Means before the solution whatever the interaction is there, after formation of solution the interaction will increases. Clear? When the intermolecular forces is greater than this case. Intermolecular force, this is after, this is before. Clear? The intermolecular forces after the formation of solution is greater than the intermolecular forces before the formation of solution. So this is the first property. Second property, delta H V mixing is less than 0. Delta V mixing is less than 0. Clear? Delta V mixing is less than 0 means what? Means before the solution, if it is 10 plus 10 20 ml, after the solution it is 19.5 ml, less than 20, less than 20, means before if it is 20 ml, before 20 ml, before the preparation of solution it is 20 ml, after the solution less than 20, less than 20 ml, okay, it will be less than 20 ml, means the delta V mixing, means after the formation of solution the volume will decreases, the volume of the solution will little bit decreases. Clear? Means whatever the delta V mixing, it will be less than 0 means negative, it means the negative means what? The volume decreases, the volume decreases. Third is the delta P mixing is also less than 0, is also less than 0. It means the vapor pressure after the formation of solution decreases, after the formation of solution decreases, solution decreases. Why? Because now the solute solvent interaction is more. When the solute solvent interaction is more, it suppresses the vapor pressure, it suppresses the vapor pressure. So that's why the delta P mixing is less than 0, means whatever the vapor pressure before the solution is prepared is always greater than the vapor pressure, greater than the vapor pressure after the preparation of solution. That's why it is less than 0, means the vapor pressure before what it is, after the solution it will decreases. That's why it is less than 0 means negative, less than 0 means negative, negative means decrease in vapor pressure, decrease in vapor pressure. And the fourth point is the delta H mixing is less than 0, is less than 0, means the delta H mixing is less than 0 means negative, delta H is negative. So when it is negative, it is an exothermic process, it is an exothermic process. The delta H mix is less than 0, it means non-ideal solution with negative deviation is exothermic process. Non-ideal solution with negative deviation is exothermic process, because the delta H mixing is less than 0. So delta H mixing is equals to negative value. Negative value means what? We know that change in enthalpy, if it is negative, then it is exothermic process, and the non-ideal solution with negative deviation will be a exothermic process. Clear? So this is the property. Let's see the example. Examples. So what are the examples are there? The first example is HNO3, nitric acid with water, nitric acid with water. Second example is phenol with aniline, phenol with aniline. And third is the chloroform, CHCl, the chloroform with acetone, chloroform with acetone, sorry, not acetone, it is benzene. Chloroform with acetone also it is possible, acetone or benzene also, clear. So these are some of the examples of what? Some of the examples of non-ideal solution with negative deviation, So now let's see the graph. Here you can see, there I have told you delta P mixing is less than 0, means the vapor pressure will decreases. So this dashed line show the original vapor pressure according to Raoult's law, but this dotted line represent the vapor pressure after the formation of solution. So here you can clearly observe the vapor pressure is less than the original vapor pressure. So that's why I have told you here that delta P mixing is less than 0, means it decreases. So from this graph it is clear that if this is the original vapor pressure, then the vapor pressure after the solution decreases from the original vapor pressure, So this is all about the ideal and non-ideal solution. Another important thing comes under the ideal and non-ideal solution. Another important concept is there that comes under ideal and non-ideal solution. So see, so start with azeotrophs. So what are azeotrophs? What do you mean by azeotrophs? This comes under the ideal and non-ideal solution. Okay, it is a special case of ideal and non-ideal, especially in case of non-ideal solution. Not in case of ideal, it comes under non-ideal solution. Azeotrophs comes under non-ideal solution. So what is azeotrophs? Azeotrophs, mixture of solution having constant boiling point. Constant boiling point. So what is azeotrophs? Azeotrophs are those mixture of solution which having constant boiling point, Clear? Which having a constant boiling point. This is known as azeotrophs. These are known as azeotrophs. Second thing is that in azeotrophs, the composition of mixture of solution in liquid phase and vapor phase remains constant. Clear? Remains constant. Understood? Equimolar. If there is equimolar amount of components are present in a solution, then what happened? That the liquid phase and vapor phase remains constant. In case of azeotrophs, the composition of the mixture of solution in liquid phase and vapor phase remains constant. So what are azeotrophs? These are two important points of azeotroph. Mixture of solution having constant boiling point, composition of the mixture of solution in liquid phase and vapor phase remains constant. It means the azeotrophs cannot be separated by fractional distillation. Fractional distillation we cannot separate. Means the two components are there, A and B. Their boiling point is different. But so what we know in fractional distillation, if there is a difference in the boiling point, they can be separated. If there is a difference in their boiling point by fractional distillation. But when there is azeotroph, in that case, what happened? We cannot separate A and B by fractional distillation. Why? Why we cannot separate the fractional distillation? Because in case of azeotroph, when they are in liquid phase, they are having constant composition. In the gaseous phase also they are having constant composition. So once they will form vapor, both component A and B will form vapor and it evaporates. It vaporizes. Okay, both will escape the liquid state. It convert to vapor phase, but they will not get separated. Clear? They will not get separated. They will escape the medium or they escape the container, but they will not separated. A and B cannot be separated by simple fractional distillation, and that is called as the azeotrophs. So azeotroph is of two types: minimum boiling azeotroph. Minimum boiling azeotroph means lower boiling point. Minimum boiling azeotroph means lower boiling point. Minimum boiling azeotroph means lower boiling point. Let's see the example. Example is if 95% of ethanol is taken and 5% of water is taken, this composition 95% of ethanol and 5% of water is a mixture of azeotrope. It is a mixture which is called as azeotrope. In this case, what happens? They cannot be separated. In this composition, they cannot be separated. They cannot be separated in this composition when 95% of ethanol and 5% of water is there. Similarly, maximum boiling azeotrope, the example is 38% of HNO3, and 62% of water. Here maximum boiling azeotrope means higher boiling point. It means that this reaction mixture, the reaction mixture of this composition, when 38% of HNO3 and 62% of H2O will be there, it will show the higher boiling point. Maximum boiling azeotrope means higher boiling point. Clear? It is higher boiling point. So in this composition, it will show the maximum boiling azeotrope. So see, when there is lower boiling point, I have told you, whenever the vapor pressure is more, at that time in class 11 I have told you, the vapor pressure when equals to the 1 atmospheric pressure, it is called as boiling point. So if the vapor pressure is more, it attains the 1 atmospheric pressure in lower temperature. It attains the 1 atmospheric pressure at lower temperature. Whenever the vapor pressure is more, we know that whenever the vapor pressure is equals to 1 atmospheric pressure, that is called as its boiling point. So suppose if the vapor pressure is more, it attains the 1 atmospheric pressure at lower temperature. So greater the vapor pressure, lower boiling point, greater the vapor pressure, lower boiling point, hence positive deviation. Greater the boiling point, greater the vapor pressure, lower the boiling point, hence positive deviation. So in case of minimum boiling azeotrope, there is maximum positive deviation. There is maximum or higher positive deviation. But when there is lower vapor pressure, when there is lower vapor pressure, what happened? There is higher boiling point. When the lower vapor pressure means it attains the 1 atmospheric pressure at higher boiling point, at higher temperature. That's why lower the vapor pressure, higher the boiling point, hence it shows negative deviation. So once again I am concluding this part. In case of we know that 1 atmospheric pressure when equals to the vapor pressure, it attains the boiling point. When 1 atmospheric pressure is equals to the vapor pressure, that attains the boiling point. So when there will be greater vapor pressure, it attains the boiling point at lower temperature, means lower boiling point, hence positive deviation. Greater vapor pressure means positive deviation. Similarly, when there is lower vapor pressure, it means it attains the boiling point at higher temperature. It means at higher boiling point the vapor pressure is low. Lower vapor pressure means what? Negative deviation. So these are the two explanation of minimum boiling azeotrope and maximum boiling azeotrope. So this is all about ideal and non-ideal solution. Thank you.